So yeah, what about quantum computing? I will try to give you a glimpse at what it is, maybe what it's not as well, and try to give you as well a few hints about how we train people and what we envision for the future of quantum computing in terms of workforce. But let's start with, well, the beginning. What about quantum? Have you ever used quantum before? The answer is yes. You probably used it this morning if you came by car and used your GPS, because GPSs are, well, timed with atomic clocks in satellites, and atomic clocks use quantum in their very way of functioning. So anyone using a GPS is using, at some point of the technology, quantum. Then what about IMR at the hospital? This is actually twice quantum, because you need quantum materials to produce the intense magnetic field in this like giant circle back there. And then it's also quantum because it will align all the spins in your body. And this spin alignment, well, spin is a quantum property of matter. In this very particular example, it's, well, the spins of protons that are aligned. And then this is quantum as well. What about lasers? Lasers used in communications these days, in optic fibers at the grocery store. I mean, you cannot explain lasers if you don't understand quantum mechanics. So quantum has already changed our lives. And this is what we call the first quantum revolution. And of course, I have this last example of the first quantum revolution. Technology here, of course, the transistors. You all use cell phones, you all use computers. And well, in order to explain how the transistors work, you have to understand quantum mechanics. So this is the first quantum revolution. We term it this way because it's when we understood what quantum was, and we use quantum to explain the physics of these technologies. The difference with the second quantum revolution is now we can control some of these properties, and this control brings us new ways of thinking about technology and new technological devices that we build. And of course, among them, there's the quantum computer. Actually, there's four main ways that quantum is being researched these days. You have the first one, which is, well, the quantum computer itself. Well, big spoiler here. The quantum computer does not work yet. So we have prototypes. We do send codes to these prototypes. We have results back. They are very noisy, and we can't actually get a quantum advantage right now out of them. But this is an active field of research, and I will jump into this field more in depth in this presentation. Then quantum materials. I've already mentioned the superconducting materials that was in the IMR. Now there is also other quantum materials that we can think of. Some are topological, so you think of the surface of some materials that will bring new ways of, well, again, controlling the matter there, and you get exotic properties that you can exploit. So this is a very, very active field of research. Actually, at Institut Quantique, it's the oldest of all these fields of research, more than 45 years. Now, quantum communication. Quantum communication will bring safety to all to all communications that we have. Quantum communication, this is actually taking place right now. We have a loop of optical fiber that will be devoted to, well, quantum communication in Sherbrooke. It will be linked to some places in Montreal, probably by the end of this year, and Quebec City will be in the loop as well before the end of next year. So quantum communication is also something of interest right now. So it's technology that is being developed as we speak. And finally, quantum sensors. This is also a technology that is being, well, transferred to commercialization as we speak. We have a great example with SB Quantum in Sherbrooke. This is a spin-off from the university, and they are working on magnetometers that are more precise than any classical magnetometers. So for measuring the magnetic field of the Earth or from, well, buried structures or eventually ores if you want to find new mines and all. So as soon as you need some very, very sensitive sensors, so magnetometers. There's also gravitometers to measure the gravity field, and there's others. Then this is a very active field as well, and closer to commercialization than quantum computing can be. But now, what will slow down this advent of the second quantum revolution? It actually is expertise. Well, quantum is hard, it's complex, but the people that can understand it and that can shape these new ideas and develop the technologies, there's not that many right now. And well, you can see from the last years a few quotes that we gathered from the internet. So we need more people in the field. And this is really what we focus on at Institut Quantique. Institut Quantique, so it's a research institute based on Université Sherbrooke. It's on the main campus. We are 8 years old now. Well, the quantum research, as I said before, at Université Sherbrooke is more than 40 years old, but the institute itself is about 8 years old. At Institut Quantique, we have this new building for 2 years now. If you ever come to Sherbrooke, come visit us. It's worth it in terms of see how research is done in, like, again, a very modern way of doing things. The Institute, it's of course, a center for having people from very diverse background coming in. There's more than 250 students that are throughout now 42 research groups. About half of these research groups are in physics, and the other half are from 6 other departments, and it's a total of 4 faculties that are represented at the Institute. So we have people from chemistry, math, computer science, engineering, politics, and finance as well, because we need all these people to look at quantum with their different and diverse backgrounds. And we have all these people coming together and work on collaborative projects. And this is really the heart of, well, I'll say any research institute, and it is particularly true for Institut Quantique. So you see a few numbers here that characterize us. Yeah, I won't go into much more details, just saying that with a CFREF grant, we've been able to launch Institut Quantique about 8 years ago, and this is how you see these numbers of $132 million, among others that have been, that provided the funding for launching the whole journey. Well, Institut Quantique in Sherbrooke, this is where the, I'd say more fundamental research take place. But then there's not just Institut Quantique. You may have heard of the Quebec government launching what they call the innovation zones. That was a bit above 2 years ago. The 2 first zones that were announced were in Bromont in microelectronics and in Sherbrooke in quantum. The third one has just been announced last fall. It's the Vallée de la Transition énergétique in between Shawinigan, Trois-Rivières, and Bécancour. This is for energy transitioning. Sherbrooke decided to propose its candidacy for quantum, which is quite bold for a city, saying, okay, we will position ourselves as the city in quantum in the whole province. So it's been accepted. And since then, there was already a pretty dynamic ecosystem there. But since then, it grew quite fast, and it's still growing. You can see, on the top right corner, I'll say, Institut Quantique with the 3IT and C2MI. So this is where the research takes place. We start with more fundamental research. We can prototype at 3IT, which is in the engineering faculty. We have all these facilities to fabricate the devices we want to test. At C2MI, which is in Bromont, we can scale up for commercialization any device that we produce in the 2 other institutes. Then we have established quantum companies. OneQubit is Vancouver-based, have offices in Sherbrooke for a bit above 4 years now. Pascal, a French company that works on a special type of quantum computers based on rubidium atoms. They now have offices in Sherbrooke, and they will fabricate their quantum computers for the North American continent from Sherbrooke. So this is taking place right now. They are building the their facility as we speak. And IBM Quantum, we've been partnering with IBM for more than 4 years now at Institut Quantique for the quantum software part. And with IBM, like in general, we've been partnering with them for much longer than that. But for the quantum computing part, more than 4 years now, they also have a IBM Quantum System 1, which is one of their largest quantum computers installed in Bromont, in their facility over there. It's the 4th IBM quantum computer in the world that is outside of the US territory. So after South Korea, Japan, Germany, the 4th one is in Bromont, and we have access to this quantum computer. We have a series of startups, either coming from the university or that are Spanish-based, Multiverse. They also have offices in Toronto. And Qubit Pharmaceuticals, this is a French startup that now has offices in Sherbrooke as well. And I won't go over all the details for the other parts, maybe just saying that in terms of infrastructure, I will talk to you a bit more about the Quantum Algo Lab, because, I mean, this is what I know the most about. So at Institut Quantique, we have what we call the Quantum Algo Lab, which is our platform of 8 quantum software developers. We are there to do research in quantum computing and support research that use quantum computing in various fields. So we right now work with people in chemistry, computer science, geomatics, biology, finance, and more. And the team is there to help the students understand what quantum computing is and to design the various projects that are good projects for for research in quantum computing. So this is, the project that I've been hired for 4 years ago, and it grew quite a bit from, 2 quantum software developers to 8 now. The Quantum Algo Lab is based on 3 pillars. I just talked about research. So this is really what we aim for, because of course we are a research institute. So of course we want to do research, in this case, in quantum computing on the software part. We also have some research at Institut Quantique on the hardware, but at Algo Lab it really is focused on software. But to do that, as I said before, quantum computing is pretty hard. We have to rethink the way we think about computing. I always say we have to reprogram the programmers. You have to think differently. You have to think based on quantum mechanics. So it's not the language itself that is hard, because we program mostly in Python, which is pretty common language for programming. So it's not the language itself, it's the way we use the computer that changes, and it changes drastically. So to do that, we have to, build a community, because there is not enough of us. So we have to, have a larger community, and we have many initiatives on that. I will come back to this a bit later. And we have to train people. We have to have more people understand what quantum computing is, and we have many initiatives on that front as well. I'll come back at the end with some examples. But if we talk a bit more about research and what quantum computing is, I won't go into all the details, but just to give you a kind of an overview, a kind of an understanding of why we look at it. I just said before, it does not work yet. So why do we do that on, our daily work? That's a good question. Let me present to you the team. We have a few members that are not there because they just joined, and we've not taken a new photo yet, but they will be pretty soon. So this is part of the team, I'll say. And quantum computing, it won't replace classical computing. I mean, what classical computers do well today, it will do well in the future. So it won't change that part. But there is some bottlenecks that classical computers have. And for some specific problems, quantum computers will be able to help the way we compute information. And not just a little bit. It's not just a new server that we would wire to our main device. It really changes everything. If we can tackle the way quantum computers work, it will be exponentially faster for these specific problems. What problems are of interest? You can see many here. Finance problems are of interest. The finance sector will be impacted by quantum computing. And this is why we have a few projects with finance researchers right now. Of course, energy, you can think of many others in this whole series of industries here. But you see kind of how people are thinking, or where the people that are thinking about quantum computing, where they're from right now. So I said that quantum computing will be useful for very specific problems. There is 3 main domains we think it will be useful for in the next probably 5, 10, 15, 20 years. So in the medium term, it's optimization. There is some ways we can think of quantum computing for helping optimization problems. Not all optimization problems, but many of them. Quantum machine learning is another active field of research. And the one that is probably the lowest hanging fruit is quantum modeling. So taking quantum environments like materials, like designing new drugs, like physics of high energy, all these fields, they are quantum in nature, and they fit well in terms of mapping these problems on a quantum computer. And this is why we say it probably is the lowest hanging fruit in all of these fields. But of course, you have noticed that there is a 4th field here in a different color. This is the quantum internet. So why is it in a different color? And I said that there's only 3. Yeah. Well, you may have heard that if the quantum computer works, this computer will be able to break the current RSA encoding that we use all the time on the internet. So the RSA encoding is based on this idea that it is very difficult to take a very long number and find its primes factors. So this is a hard problem, and this is because it's a hard problem that we say that internet right now is safe. But the quantum computer will be able to factorize large numbers into their primes very easily, and we already know the algorithm that will be able to do that. So in this case, the quantum computer is the threat. And there is some ways we can think of for protecting ourselves. There is right now a lot of research in that field. The NIST, so the standard organization in the US, is already working on many new ways of encrypting information. There is 3 or 4 protocols right now that are under intense investigation, and there's more and more that are proposed every year. That started many years ago, and it is in process so that we can protect our data that is right now available with encoding that will protect us from eventual quantum computer attacks. So in this case, the quantum computer is not the answer, it's the threat. And this is why we won't take it into the domains of quantum computing, just because this is not what interests us at AlgoLab, but it's not because it's not of interest. We have to think about it. People think about it, and we have to find ways, either classical or quantum. There's classical solutions, there's quantum solutions for that, and there's active research on that field. If I give you a few examples of projects that we worked on before, we partner with the Bank of Canada that was a fun project. It was to see, okay, the bank has to deliver these new bills to their regional facilities before they are distributed to the various banks throughout the country. So the idea is to have the best routing for the truck. So it's not just a traveling salesperson problem, it also is a knapsack problem because the truck itself has a finite volume. So you cannot put more than X number of new bills in the truck because it will just spill out. So how do you plan your routing with this finite volume and trying to find the best way to minimize the distance that you will run? So that was an optimization problem based on an algorithm that we call QAOA, the quantum approximate optimization algorithm. And if you are interested in more details about this project, I can talk to you after the presentation, of course. Other examples, we worked with the RDC, so our Defense Research and Development for Canada organization. We worked with them on a roadmap for adoption of quantum computing. That was a few years ago. And of course, the RDC is very interested in knowing how to use quantum computing and how to make it a reality into their daily work. We also worked with Statistics Canada. That was a quantum machine learning project that explored 3 ways of classifying text. The pretext, and I will say pretext, was to differentiate the text from barcodes used in grocery stores. The idea here of the pretext is that whatever the data, today there is no quantum advantage, again, of using the quantum computer, but the idea is to see what would be something interesting and what would be scalable once we have a, fully functional quantum computer. So that was a short 6-month project, very interesting. We learned a lot with them, and the idea right now, again, is to learn and eventually design new algorithms. With Lockheed Martin, that project was pretty close to the core of the quantum computers. Right now, the quantum computers, they don't work for long. After a very short period of time, we lose the quantum coherence. So that means that we lose all the quantum information that we store in the computer. And when I say it's short, I mean it's a few hundreds of microseconds. So it's not yet the millisecond long. So it's very fast computation. And we need to apply all our logic to the qubits, the quantum bits. So it's the quantum information unit within the quantum computer. And we have to be very, very efficient in doing so. And if we want to manipulate the qubits, we have to be efficient as well. And by working on the pulses that we send to the qubits, we can be more efficient than less with native pulses. So that project was to find new ways of optimizing the pulses. We used some machine learning for that. And we've been able to, have a duration that was up to 73% shorter than what was originally there. That means that we could manipulate more of these quantum gates and have a deeper circuit, which is what we are looking for right now. With Thales, we have a project right now with them. That was the small project that was just before. It was a time series classification. The idea was to look at quantum machine learning approaches using reservoir computing. It was really just for starting a project with them. A small 6-month project that we knew was just a bridge to this larger one right now that we're working with them. It's a project right now in detecting anomaly in communication signals. And so, it gives you kind of an idea. I don't want to go in more details into all of these specific projects, but I wanted to give you an idea of what is the type of project that we can work on right now in quantum computing. And as you can see, we do that either with researchers within the university, or we do that with external partners as well. That is a project that we had with finance researchers at the university. If you want to have more details, again, I invite you to come to see me at the break, and I can talk to you more about this one. I told you before, we have 3 pillars at the Algo Lab. So research is one, very important. We have also building a community and training that is very important to us. This is on the training front. We have many workshops that we deliver. The intro workshops that you can see here, so number 1 and 2, have been delivered to, various CEGEPs throughout the province. For 4 years now, we've met with more than 1,000 and a few hundred students. We also have delivered these workshops in the industry. You can see a few of the partners we've worked with before. And number 3 to 6 right now are more in, intermediary level workshops that we also have built. We have more advanced material, but the more advanced material so far has been just delivered to university students, so either at Sherbrooke or in other universities. But the idea, again, is to have more students understand quantum computing, at least be introduced to what quantum computing is. And the same with industry partners. When the partners are interested in knowing what quantum computing is, well, we have to find a way to help them understand, to train their people, and this is a good way to do so. Other than that, well, a very important task that we have is to manage expectation. People are excited about quantum computing because it is an exciting field. We are like very, very happy of doing that again every day of our lives. But because the quantum computers don't work yet, we have to be realistic about what we hope from them on the short term, at least. So right now, quantum computing is a strategic initiative. You won't have no return on investment on a 1 or 2 year horizon as we're used to in high tech. It probably is more 5, no, not 5, 10, probably 10 and more. And I say 10 and more for 4 years now, just to tell you where we stand. So this is on the hardware front. Then the second part here, on the software front, there is so much to work on. There's so much to discover. There's so much to put in place. We know many primitives. We know many algorithms, but not everything has been discovered or invented yet, and that we have to work on as well. And finally, because quantum computing is hard and complex, we have to train our people and have people ready for when the hardware will be there and ready to be used. And to do so, we have what we call our pipeline of talent, and we thought of a pipeline to, well, picture it, as you can see. And we divided it, on the long term, midterm, and short term. So on the long term, we go to high schools and CEGEPs. This is the project that we call Curieux Quantique. We also, with Curieux Quantique, have many educational outreach initiatives for the general public. On the midterm at the university, we have a bachelor's degree in quantum information science. Sarah Blanchette here in the room will be on the panel a little later this morning, and she will tell you all the secrets about the bachelor's degree since she's the executive director of this degree. This is actually the first degree in quantum information science in French in the world, and probably something like the 5th one, all languages accounted for. And we have many graduate studies paths at the university that you can take so that you incorporate some quantum into your graduate work. Then on the shorter term with the Algo Lab, we work for, individuals that would like to, either learn more about quantum computing or that want to reorient their careers. So we have many things that we can do with these professionals. We have a few workshops that are intended for engineers that are coming by mid-April, and every second week there will be other workshops. So if you are interested in that, if you are an engineer, you're welcome to come to these workshops. Otherwise, you saw our offering for industry and government as well, and we have to work on, again, developing the pipeline of talent. So this is what we do at the university. There's, of course, many more initiatives. ETS in Montreal has many, Concordia has some as well, and of course in the rest of Canada there's many things taking place. A very interesting professionalizing master's degree in Calgary right now that is being put together. And this is just to name a few. There's more than that. Otherwise, on the community building side of things, we have external tech meetings for people that are already into quantum computing. So this is not for, training. This really is, experts meeting experts. We have an internal tech meeting every week, and then we decided a year ago to open it once a month for our partners as well. And this is where it all takes place, I'll say. We also have people from the industry, mostly from the hardware companies that also have some research in the software that come from time to time. Otherwise, it's people with actual research that present their work. Very interesting meetings there. So we have a Slack channel to accompany that, open house or once a year. We also have a hackathon, and that I can maybe give you an idea of what it looks like. That was in Sherbrooke last October. We had 93 people from 9 companies, 15 team competing. So the morning was to learn about what quantum computing is, and the afternoon was while trying to tackle challenges that we threw at them. If you are interested in our next edition of the hackathon, you can contact me at the end of the conference, and I can have you on a waiting list for receiving all the details. It will probably come back next fall. Exactly for all the details we don't know yet, but we know it's going to be probably in October. So coming again this year. Otherwise, we also have worked on educational material that was intended at first for CEGEP students, but we've used that in high schools as well and at the university level in intro courses to quantum computing. The Quantum Enigmas, it's a series, well, right now you see 8 different videos. There's 11 that are now out, and there's a 12th one. It will be a series of 12 videos. Basically, they are animated videos between 7 and 10 minutes, and we use classical enigmas that we map on the quantum computer, and we solve them using the logic of the quantum logic gates, but without using math and without using Python programming. So it really is just the logic of the gates that is used to, introduce how we think differently about quantum computing. There is no quantum advantage in doing so, but it really is a fun way to learn, what it may be working on a quantum computer. And of course, after the series of 12, there is many more resources on the web that you can use. We also have developed some modules that are interactive module or exercises based on the enigmas that we have worked with IBM Skills Build, which is a platform for learning high-tech fields. There are some things in cloud computing, cybersecurity. There was not much in quantum computing, and we decided to work with them for working on for developing these modules based on the quantum enigmas. This is intended for high school students. And we are very proud to say that the Enigmas have been awarded the Canadian Applied Arts Award last year for the quality of their images. And this is, thanks to Studio Nord-Est, a Quebec City-based studio that works on all the drawings and the animation for the videos. And with that, I hope that you grasp the idea that, quantum computing is hard and that we have to develop more and more talent. If you have any question about any of these topics that I covered today, you're welcome to ask them now.
My question is, I have 2 questions. One quick one. Which high school subject do you think is most important to building quantum talent in the long run? So if you had to double the investment in one subject like English, chemistry, physics, math for high school students, which one would you choose?
Wow, that's a good question. Quantum computing is based on 3 pillars. The name suggests it, quantum and computing. So quantum is the physics part, computing, of course, computer science. But then what's the third part? Math. And it really is the 3 of them that makes up quantum computing. So if I talk about quantum computing, because quantum at large, that may be more physics, but for quantum computing, it really is the 3 pillars. In the team, most of the people come from, 2 of the 3 fields, and anyone that came in the team had to learn the third one. And this is what we have to do today, is to really share knowledge, share how we understand quantum. So this is, of course, more advanced than just, than the high school level that you asked about. But the idea is the same. Quantum computing is great for math teachers because there's all the probabilistic approach that they can use and talk about probabilities in a fun way, because quantum computers will use probabilities in how they function. Then, of course, on the physics side, you can introduce some concepts of superposition, entanglement, interference, and so on. So it's quite enjoyable for students, and they always love it when we do so. We have many demos that we bring to high school students as well, and it makes it fun to learn about quantum. And on the computing side, I mentioned it briefly with the quantum enigmas. You don't necessarily need to program in Python. You can use what we call the quantum composer. So composer really is like a music composer. You start with 1 line per qubit, and then you simply apply quantum logic gates to your circuit, and this makes up your algorithm at the end. And you can think of computing using just this composer, which could be kind of an equivalent of Scratch in classical, but for quantum. So there's many things you can think of at the high school level, while introducing quantum knowledge.
And the second question would be, governments across Canada have been investing in building the quantum talent pool for a while. I know that there's the Quantum Algorithms Institute at SFU, and that's been going on for a few years now. What's been the most surprising challenge in building the talent pool that none of you guys saw it come in?
The greatest challenge in training would be everything. I mean, having interest from the students, this part is kind of easy, I'll say, because again, we can introduce in a fun way what quantum computing is. But even with the quantum enigmas, for example, I always tell that quantum enigmas are the second step in quantum computing. So first step is to learn what is a qubit, what superposition, entanglement, interference are. So these are really the building blocks of the quantum computer. And then once you grasp kind of an idea of what all that is, then you can, use the quantum enigmas. But then very soon, what you will face is the complexity of the math that goes behind it, of the programming that will accompany this math. And of course, what you have to do is figure out how can you maximize, the NISQ systems that are the near-term intermediate scale quantum computers. So these systems that are very noisy that we have right now. Or the other thing the other path you could use is to say, okay, I won't bother about NISQ. I'm not interested in just trying to get out, things from something that, does not work anyways. And I will work for the fault-tolerant quantum computer that will come in a few years or decades from now. But then you will work only on theoretical material. Maybe you will be able to send a few lines on simulators, but classical simulators past 50 or 100 qubits, they are not working anymore. You have to have all these approximations taking place. And this is why, the actual quantum computer will be so much more powerful than the classical computers for these calculations. Is because it will be presenting an exponential advantage or runtime over the classical computers. So you can't simulate with a classical computer what will be better on a quantum computer. Of course, at some point there is a limitation there. Yep. Other questions?
Can I? Yeah. Hello, my name is Bastien. I've been in the industry of quantum for a year now, and I can testify that it's a very different industry, very complex. And congratulations on the presentation. You made it pretty simple, and congratulations on the Institut Quantique. They've been doing a colossal work around the world. I must say it's very respected. Now, for people who don't have a science background, who would like to be involved and would like to discover quantum and do projects, what would be your best advice how to address this industry and how to address these projects? Thank you.
Well, for the research itself, I'll say you need a scientific background. I'm from science, but not from physics, nor math, nor computer science. I'm from geology, and I'm not doing the research. So I do evolve in the field of quantum for 4 years, but with a different role, which is partnerships and also this managerial part of the work with the two teams of the Quantum Algo Lab and Quantum Curious. So for people that are scientists, I say there is a place, but it won't be in the research itself. It will be in other very important roles, but it will be in roles that are revolving around, the research. For the research, you'll need to be, again, scientist, and you have to, go deep into the physics of it and into the science of it. Yeah.
Thank you, Tim. Thank you, Ghislain, for a beautiful presentation. I was not expecting to see the procession of spins, so I was really excited. But something that I've been really impressed by the University of Sherbrooke is their commitment to sustainability. Like they've been #1, really innovative with their innovation park. If the quantum computer is successful, what will be the impacts or ties to sustainability?
Can you repeat the last part,
Yeah.
please? Yeah.
If the quantum computer is successful,
Yeah.
how does it relate back to sustainability of the environment?
Okay, thanks. Well, there's many ways we can think of using the quantum computer for sustainability. Right now, there is an international working group in sustainability that has been put together by IBM. We are part of the founding members of this group as well. There's Pink, the platform that manages the IBM Quantum System 1. It's a nonprofit that is based here in Quebec, but it's for whole Canada for accessing the IBM quantum systems. So they are part of the working group as well, and there's many other organizations. And the idea is to look at how exactly that question can be answered. So how can we use a quantum computer for sustainability purposes? Right now, we have projects in, I'll give you more, detailed examples here. We have a project in biology that looks exactly at that. So the idea is to see how can we use the quantum computer for biology or ecology problems that are not possible to tackle with classical computers these days. We have projects in chemistry that go along these lines as well. It's in quantum materials. So how can we design better materials for batteries, for example? And this is something that, again, the quantum computer will be good at in terms of capacity. And there's others. I think of geomatics, for example. You can think of prediction modeling of natural disasters, and this is the type of things that quantum could help at some point in the time. So there is many things and many ways we can think of it. So yeah, the university is engaged in this sustainability process, and quantum computing is part of the tools that we have, or hope will be helpful to pursue that goal. Yep. Well, I guess that's it. So, thank you very much, everyone, for attending this morning. And, if you have other questions, I'll be here at the break.